All right, in this video, I want to take a minute to talk about a feature that is on the Freedom Auto boards. And it's something you may or may not have learned in school. I know when I went through school, they're touched on lightly, but we didn't use them as much as we could have. But I use them quite a bit in industry. And that is of what we call an optocoupler. Now, optocouplers are very important in industrial control and electrical control and interfacing because they have a very, very important feature in that they provide what's called galvanic isolation. And you can go search on what this means. But what that essentially means is that we can isolate one electrical domain from another. And that's a very, very powerful thing to want to do, is have some signal in one domain and move it to the other so we can add like a layer of safety, first and foremost, and also things like noise immunity. And it helps us decouple one circuit from another. And so one kind of circuit we have is an optocoupler. And we have one right here. This is a MOC D207M. Now, optocouplers come in many shapes and sizes. So this is just one, and we're going to look at kind of like two different ways of doing it. And the other one is we're going to look at an optically controlled solid state relay. It's kind of like the same but different. And we're going to look at one that's fairly similar. Now, this one, you can see that it looks like there's two of the same kind of thing inside that package. So we have two optocoupled inputs. Now, the simplest optocouplers on one side have a transistor. We can see it right here. And on the other side have an LED. All right? And inside we have this, they usually draw it as like a dashed line. We have a barrier of isolation. And what's kind of nice is that everything that happens on this side of the circuit can be electrically, we'll say, decoupled or isolated from this side. And that's a beautiful feature about an optocoupler. So here's how they work. On the right-hand side, we have a transistor. Now, this transistor works, think of it like any other transistor you've ever used, like a 2N222. You can look on the data sheet for parameters such as how much current they can handle and whatnot. And you notice I have this wired up as an open collector output. So what that means is if this transistor is not turned on, think of this as this switch is off. And if that switch is off, this point here floats to 3.3 volts. I should say floats. It gets pulled up to 3.3 volts. All right, let's start fresh here. So here's the way this works. First, step one. We can put current into this diode, just like that. Whenever you run current through an LED, we get light. Now, the way an optocoupler works is that light is directed at what we'll think of as the base of this transistor, and through the photoelectric effect, we get base current. And remember, with base current, we get collector current, right? Because it's current to current. That's how a BJT works. And so in this configuration, if we put current in this way, we get current through our 7, and this has the effect of turning on this transistor and bringing this point here to ground. It goes low. So if we put current in this way, this goes low, and when there's no current, this transistor is off, meaning this point then floats up to 3.3. Or, I'm sorry, gets pulled up to 3.3. All right? Simple enough. Now, to get current through an LED, we have to forward bias it. And the way you forward bias it, you just need either a current source or voltage source. In this case, if we apply something here, all right, of enough potential, we can get current. Now, the current in this case is limited by this 15K resistor. Now you also notice I have another diode in the path here. And we're going to take a look at and a reason why. So let's just pretend it's DC. So let's say we apply plus here and minus here. That would forward bias this circuit and turn this circuit on. And so what's neat about this is that the potential from here to here that turns on this LED no way affects the electrical. This potential is in nowhere referenced to this potential with respect to ground. So this lower potential here minus this ground, we'll call it ground, is in no way coupled to this one. And that's very powerful. In electrical networks and industrial networkings, that's a very nice feature, to have. Now, so why this diode here? Well, it is possible to flip the polarity, to put minus up here and plus, and in that case, this diode would normally block it. Well, if you look at the data sheet for the this MonkeyDo 207, it doesn't have a ton of reverse bias protection. It will eventually avalanche and break down. Well, the reason I wanted this diode here is that what if, let me get a different color, and I'll draw it down here, we wanted to directly feed 120 volts AC to detect an AC signal. Well, in that case, if this was, say, like 120 volts AC, the reverse potential, if I had plus here and minus here, is quite large, and we could damage the device. So this here is what drops all the voltage, and this one is rated. The RS, I want you to look it up to see the rating. You'll see that this is rated to handle the reverse voltage of the reverse potential if we were to plug into 120 volts AC. So what we really have here is if you were to probe at this point, we would have half-wave rectification. All right? And so the size of this resistor is then set for the peak current generated by the peak voltage here. Because I believe we need 10 to 20 milliamps of current to fully turn on the transistor. Now, keep in mind, these things do work in a linear range. You can actually use these where, like a transistor, where you can slowly increase the current and then you can kind of bring down this voltage here. And just use it in linear mode. Now, in this case, we don't really care. This is kind of tuned that this transistor will fully saturate if you put AC in. So what you essentially get is if you're going to put AC in on this side, and let's say this was 120 volts AC, on this side of the world, and I'll draw it in different, you would get a square wave because, you know, when this goes on, this goes off, and when it goes the other way, it goes the other way here. And so the frequency would be 60 hertz, all right? So that's the caveat here, is that if you want to use this circuit to detect AC, this point here is going to toggle at 60 hertz. Now, what if you didn't want that? Well, a couple of things you could do. You could use a timer on the microcontroller to measure it to know that you are getting 60 hertz versus DC. Because if you were to put like a DC potential over here, it would just be always on. But maybe you want to measure frequency. Now, let me show you a little hack you can do. Is if you don't want to have to deal with the DC, or I'm sorry, the square wave. So let's clean it up again. We can do one special thing here, and let me draw it. We can add a capacitor right here. Because if you think about this, this is almost works just like rectifying a power supply out of a transformer. So just adding the diode gets us this, right? And if we pick our capacitance correctly and make it large enough, what will happen is it'll charge up, slowly decay, charge up, slowly decay, as long as we have an AC input. And then if our AC input goes away, what will happen is we'll slowly decay away. Now you have to pick this value of capacitance dependent on the load to get this timing right. And I'll let you do that as an exercise. But I can pretty much guarantee you just pick, because this is not a whole lot of current right here, so you don't need a ton of capacitance. So you don't want a lot of capacitance. You don't want to pick like 500 microfarad or 470 microfarad, because even after you remove this, you'll have a significant decay time. But you want enough to smooth out the humps. That's a way to one more hack you could add into this circuit that would be pretty easy to do. But if not, you can use it as is, or you can use it in DC. So optocoupled inputs are very common in any sort of industrial networking, industrial control, process control, because we can kind of decouple one electrical domain from another, and we're using light as the intermediary. So I hope this is helpful, and tune in for some more videos on the MonkeyDo project.